तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the 6th lecture of Module 5 on Analysis and Design for Shear and Torsion. In this lecture, we shall study about design for torsion. We shall first study the detailing requirements. Next, we shall move on to some general comments, and then we shall learn about the design steps. First, detailing requirements for torsional reinforcement. The detailing requirements for torsional reinforcement in clause 22.5.5 IS 1343-1980 are briefly mentioned. The stirrups should be bent close to the compression and tension surfaces, satisfying the minimum cover. There should be at least one longitudinal bar in each corner. The minimum diameter of the longitudinal bar is 12 millimeters. Thus, we are trying to have the stirrups as close to the periphery as possible. We shall of course have to satisfy the minimum cover requirements, and we have to hold the stirrups by the longitudinal bars. The longitudinal bars have to be stiff enough to keep the stirrups in position, and hence the minimum diameter of the longitudinal bar is recommended as 12 millimeters. The second requirement is the closed stirrups should be perpendicular to the axis of the beam. Closed stirrups should not be made of pairs of U stirrups lapping one another. As we had known earlier, that for torsion we need closed stirrups to resist the circulatory shear. The closed stirrups should be perpendicular to the axis of the beam, and also the closed stirrups should be made of only one piece of steel bar. We cannot make closed stirrups by overlapping two U bars, although that is more convenient in construction. We should make the closed stirrup by one piece of a reinforcing bar, as shown in the figure. That means the figure on the left is an incorrect detail because they are using two U stirrups overlapping each other, but the correct detailing is to have one piece of stirrups with proper anchorage at the ends. The third requirement is the maximum spacing is x1 plus y1 divided by 4 or 200 millimeters, whichever is smaller. Here x1 and y1 are the short and long dimensions of the stirrups respectively. This requirement has come from the space truss analogy that the stirrups should traverse all the inclined cracks, and based on that requirement, the maximum spacing is x1 plus y1 divided by 4, where x1 is the smaller dimension of the closed stirrup and y1 is the larger dimension, and there is an upper limit to this expression which is 200 millimeters. The fourth requirement is related with the anchorage of the stirrups. The ends of the stirrups should be anchored by standard hooks. That means that unless the stirrup is properly anchored at the ends, it will not develop its yield stress. Hence, proper anchorage is necessary at the ends of the closed stirrups. It is recommended to bend the ends of stirrup by 135 degree and have 10 times the diameter of the bar, which is represented as dB, as extension beyond the bend. That means one end of the bar has been bent by 135 degree and it has been inserted within the core concrete, and the other end of the bar is also bent by 135 degree and inserted within the core concrete. The extension of the bars beyond the bends should be 10 times the diameter. This detailing helps to restore the shape of the stirrups under torsion. That means the stirrups has to be in the original form when the torsion is acting. That stirrups should not open up in presence of torsion, and to maintain this shape, the ends of the bars are provided with 135 degree hooks, and the extensions beyond the hooks are placed within the core concrete. The fifth requirement is the stirrups should be continued till a distance d plus bw beyond the point at which it is no longer required. Here d is the overall depth and bw is the breadth of the web. This requirement has also come from the space truss analogy, that after the concrete forms struts and the steel bars form the ties tying the concrete struts, the stresses that we calculate at one particular section is in fact shifted due to the formation of the struts, and based on this reason it is recommended that the stirrups have to be continued beyond the point of calculation by a distance d plus bw. This is to maintain the truss action in the resistance for torsion. Next, we shall be discussing some general comments in the design for torsion. The restraint to torsion is provided at the ends of a beam. For beams in a building frame, the restraint is provided by the columns. Precast beams are connected at the ends by additional elements like angles to generate the torsional restraint. In bridges, transverse beams at the ends provide torsional restraint to the primary longitudinal girders. Box girders are provided with diaphragms at the ends. Thus, what we can see is that the beams that are subjected to torsion need to have some restraint at the ends to resist the torsion. For individual beams like a precast beam, torsional restraint is provided by some attachments at the ends like angle attachments. In bridges, there are transverse beams are provided, or in a box girder, diaphragms are provided at the ends to provide the torsional restraint. Thus, when there is a torque acting along the length of the beam, the restraint comes from the two ends of the beam. For equilibrium torsion in a straight beam with distributed torque Tu, the maximum torsional moment Tu is near the restraint at the support. This figure shows a beam which is statically determinate and it is subjected to a distributed torque Tu per unit length. In this beam, the maximum torque comes at the two ends near the restraints at the support, and that is denoted as capital Tu, which is the maximum torsional moment acting in the beam. L is the clear span of the beam. The torsional moment near the support is given by the following expression: capital Tu is equal to the small tu times L divided by 2. Here L is the clear span of the beam and small tu is the distributed torque per unit length of the beam. For a straight beam with a point torque, the maximum torsional moment Tu is near the closer support. If the location of the point torque is variable, Tu is calculated for the location closest to a support. The analogy can be drawn for shear that when there is a variable point load, the shear is designed for the location of the point load which generates the maximum value of the shear. Similarly, for torsion, if it is generated due to a point load and if the point load is variable, such as the vehicle load in a bridge, then the maximum torque is calculated by placing the point load at the position which generates the maximum value of the torque. The point load has to be placed closest to the support to generate the maximum torsion in the beam. In a curved beam, the calculation of Tu is more involved. It is calculated based on structural analysis. Next, the design is done for the critical section. The critical section is defined in clause 41.2 of IS 456-2000. In general cases, the face of the support is considered as the critical section. When the reaction at the support introduces compression at the end of the beam, the critical section can be selected at a distance effective depth from the face of the support. Thus, although the maximum torque occurs at the face of the support, if the support is under compression, then we can select a section which is at a distance effective depth from the face of the support as the critical section, because the concrete in between the section at a distance effective depth and the face of the support is under compression and its capacity is larger as compared to the rest of the beam. Hence, the critical section can be selected at a distance effective depth from the face of the support. To vary the amount of reinforcement along the span, other sections may be selected for design. Usually, the following scheme is selected for the stirrup spacing in beams under uniformly distributed load. Close spacing for quarter of the span adjacent to the supports, wide spacing for half of the span at the middle. For large beams, more variation of spacing may be selected. Let us understand this by a sketch. In this figure, you can see that the spacing of the stirrups at the two ends is close, whereas the spacing at the middle half of the beam is wide. Hence, if we want to vary the spacing of the stirrups, then we have to select more than one section for design. And in this situation, at least we need two sections. One is the section which is at the effective distance from the face of the support, and another section is at a distance quarter of the span of the beam. Next, an equivalent flexural moment mt is calculated from Tu. Thus, once we have calculated the torsion demand Tu, from that we are calculating an equivalent flexural moment mt. For the design of primary longitudinal reinforcement, including the prestressed tendon, the total equivalent ultimate moment mu1 is calculated from the flexural moment mu and mt. We have the flexural moment mu and we have the equivalent flexural moment mt due to the torsion. We add these two up to get the total equivalent moment, which is ME1, and with that we design the primary longitudinal reinforcement including the prestressed tendon. The design of longitudinal reinforcement for other faces based on equivalent ultimate moments ME2 and ME3 is necessary when the equivalent moment MT is larger than MU. Thus, if the torsion is substantially high, then we may need to design for the other two equivalent moments ME2 and ME3 that will provide us designed longitudinal reinforcement at the other face. This figure shows the three design moments. The first one is ME1, which is in the same sense as that of the flexural moment, that if the flexural moment causes compression at the top, ME1 also will cause compression at the top, and the value of ME1 is larger than the flexural moment due to the effect of torsion. Second, if the torsional moment is substantially high, then the failure may occur by the crushing of concrete at the bottom and yielding of the steel at the top. To check such a case, we design for a moment ME2 which generates compression at the bottom and tension at the top. Observe that this is in an opposite sense to that of the flexural moment MU. And the third one, which is usually governed in the flange sections with thin web, that we may have to design for a moment which occurs about a vertical axis to cause transverse bending. This moment ME3 generates compression at one side face and tension in the opposite side face. Thus, the axis about which ME3 acts is vertical, unlike that of ME1 and ME2. Observe the orientation of the three design moments for the design of torsional reinforcement. The design for ME1 is similar to the design of a prestressed section for flexure. Earlier in the chapter of design of members, we had studied in details the design of members for flexure. In presence of torsion, once we calculate ME1, the design is exactly similar to what we had studied for flexure. The design for ME2 is similar to the design of a prestressed concrete or reinforced concrete section. ME2 is the negative bending. We can design the section either as a reinforced concrete section if we do not have prestressing steel at the top, or else we can design the section as a prestressed concrete section if we provide some prestressing steel at the top. And the third, the design for ME3 is similar to the design of a reinforced concrete section. For the transverse bending, we design it like a reinforced concrete section. The design of stirrups, including torsion, is similar to the design of stirrups in absence of torsion. Again, in the design for shear, we had studied how to calculate the steel and provide the spacing. When there is torsion, the design is similar to the procedure that for shear, except that the expressions of the amount of torsional reinforcement and the spacing is different when there is torsion. The following quantities are known at the selected section: Mu, which is the factored flexural moment; Vu, the factored shear; Tu, the factored torsional moment. For gravity loads, these are calculated from the dead load and live load. Thus, before we start the design, from structural analysis, we have calculated the three actions acting in the particular section, One is the flexural moment mu, next is the shear Vu, and the torsional moment Tu. These are the known quantities before the design of the section. The grades of concrete and steel have to be selected before design. As per IS 1343-1980, the grade of steel for stirrups is limited to Fe 415. The selection of the material properties depend on what material will be supplied, and also it depends on the type of structure that is being built. Before we start the design calculations, the material properties should be known to us, and hence we can use those properties in the design equations. For the design of longitudinal reinforcement, the following quantities are unknown: the member cross section, then Me1, Me2, Me3 total equivalent flexural moments, AP, which is the amount of pre-stressing steel, PE, the effective pre-stress, E, the eccentricity of CGS with respect to CGC, AS, area of longitudinal reinforcement, AS prime, area of longitudinal reinforcement in opposite phase, and pre-stressing steel AP prime may be provided in the opposite phase. If Me2 is large, then we may provide pre-stressing steel at the top also and design the section as a pre-stressed section. Thus, again, before the design, we know what are the unknown quantities that we need to solve to come to the designed section. For the design of stirrups, the following quantities are unknown: Vc1, which is the shear carried by concrete, Tc1, which is the torsion carried by concrete, ASV, which is the total area of the legs of stirrups within a distance SV, and SV is the spacing of stirrups. When we are designing the stirrups, first we need to know the capacity of concrete to resist shear, which is Vc1, capacity of concrete to resist torsion, which is Tc1, and then we need to know the area of the stirrups, which is ASV, and the spacing of the stirrups, which is SV. Remember that Tc1 and Vc1 are the reduced values from the capacities under the individual actions. Next, we shall discuss about the design steps for the torsional reinforcement. The steps for designing longitudinal and transverse reinforcements for beams subjected to torsion are given. First, calculate Mu, Vu and Tu at a selected location. These are the design forces at ultimate for the location that we have selected. Next, select a suitable cross section. For high values of Tu, as in bridges, a box section is preferred. The selection of a section was discussed when we studied the design of members. The selection depends on the application and it depends on the relative values of the forces. In buildings, usually we have rectangular sections, or we can have flange sections made up of precast beams. For bridges, we can have rectangular sections for small span bridges, but as the span increases, we prefer to have eye girders, or if the torsion is high, then we select box sections. Thus, the selection of a section is important, and it is as per the application and the design forces acting in the particular beam. The next step is to calculate the equivalent moment Me1. Me1 is equal to Mu plus Mt, where Mt is calculated from this expression Mt is equal to Tu times root over 1 plus 2d divided by b. mt is the equivalent flexural moment corresponding to the torsional moment Tu, and we add that to the flexural moment mu to get the total equivalent moment at ultimate, which is represented as me1. The geometric variables are defined for the different types of sections as follows. B is the breadth, and which is the smaller dimension, and d is the depth, which is the longer dimension. For a hollow rectangular section, the thickness should be at least quarter of the breadth, so that we have adequate shear flow zone in the hollow section. For a flange section, the breadth is the breadth of the web, which we substitute in the previous expression. The second step, we have the design AP and AS. AP is the amount of prestressing steel and AS is the amount of longitudinal steel. The design procedure involves preliminary design and final design, which were explained under the module of design of members. Thus, the flexural design is a systematic procedure to select the appropriate section and to select the maximum eccentricity of the prestressing steel, and also to have the amount of prestressing steel which is economical. This we do by having the maximum possible lever arm at service loads, and this design steps for the are divided into two stages. First is the preliminary design stage and second is the final design stage, and we discussed about these two stages in the module of design of members. Thus, even when the member has torsion, the design of the primary longitudinal reinforcement is exactly the similar as the design of members for flexure. The only difference is we are substituting the total equivalent moment me1 in place of the flexural moment mu. The third step is calculate the other equivalent moment me2 if mu is less than mt. me2 is equal to mt minus mu. Thus, if the torsion is substantially high, there is a chance of a negative bending failure, and in that situation we need to calculate me2 and design for me2. Design AS prime for me2. The design procedure is similar for a reinforced concrete section. If AP prime is provided, the design is similar to a prestressed concrete section. Thus, once we have me2, we can design the section as a reinforced concrete section if we do not provide any prestressing steel at the top near the tension zone. If we provide prestressing steel at the tension zone, then we have to design the section as a prestressed concrete section, and the design procedure is similar to the design for flexure. The fourth step is to calculate the third equivalent moment me3 for transverse bending if mu is less than mt. Thus, expression of me3 is given as follows: mt times 1 plus x1 divided by 2e whole square times 1 by 2b divided by d whole divided by 1 plus 2d divided by b. This is an expression of a moment which acts about the vertical axis and causing transverse bending. And since it causes transverse bending, we need to design for the side face reinforcement. Remember that we need to do only if the torsion is high with corresponding to flexure. In this expression, E is equal to Tu divided by Vu. Note that this E is not the eccentricity of the prestressing steel. Here E is the ratio of the ultimate torsional moment to the ultimate shear, and x1 is the smaller dimension of a closed stirrup. Thus, for a closed stirrup, we are representing x1 as the smaller dimension and y1 as the larger dimension. Once we have calculated ME3, we need to check the adequacy of transverse bending based on the corner bars. If inadequate, design side face reinforcement AS, SF, and AS, SF includes the corner bars. Thus, once we have calculated ME3, we are checking whether the bars which have been provided at the corners is adequate to carry this moment. If they are not adequate, then we design extra reinforcement for the side face, and the total side face reinforcement is represented by the notation AS, SF, and this design is done similar to a reinforced concrete section. To recollect, for a singly reinforced rectangular section, the amount of longitudinal reinforcement AS is solved from the following equation: 0.87 times Fy times AS times the effective depth D times within bracket 1 minus Fy times AS divided by Fck times the breadth B times D equal to Mu. The values of the breadth B, effective depth D and design moment Mu are appropriately substituted. Here we wrote the expression of a singly reinforced section, and once we know the moment, we should appropriately substitute the values of B and D, remembering that it is a transverse bending. That means here B will be in fact the vertical dimension of the beam and D will be the horizontal effective depth of the reinforcement. Substituting these variables appropriately and the moment, we can find out the value of AS. Next, we are moving on to the design of transverse reinforcement. The first step is to calculate the capacity of concrete to resist torsion. TC is given as summation of 0.15 B squared D within bracket 1 minus B divided by 3D times lambda P root over FCK. Lambda P is equal to root over 1 plus 12 FCP divided by FCK. Last time we saw that the capacity of concrete is based on the generation of a torsional crack at the mid depth of the longer side. If it is a flange section, then the expression considers the flange section as a compound section made up of several rectangles, and we use the summation symbol. The effect of prestressing is considered by the factor lambda P, which shows that with increasing prestress, the strength of concrete will increase, and this expression of TC helps us to calculate the capacity of concrete to resist pure torsion. Calculate Vc, the capacity of concrete for shear in absence of torsion, from the lower of Vc0 and Vcr. To recollect, Vc0 is the capacity of concrete for an uncracked section. Vc0 corresponds to the shear which generates a web shear crack, and Vcr is the capacity of concrete for a cracked section. It is equal to the shear that causes a flexure shear crack, and the expressions of these two quantities Vc0 and Vcr as follows: Vc0 is equal to 0.67 Bd times root over Ft square plus 0.8 Fcp times Ft. Now, in this expression, Ft is the tensile strength of concrete and Fcp is the average prestress at the level of the CGC. The expression of Vcr contains two terms. The first term is the amount of shear that extends a flexural crack to a flexure shear crack, and this term depends on tau c, which is the capacity of concrete to resist shear, and the second term is the shear which generates a flexural crack. The value of VCR need not be smaller than 0.1 BD root FCK. Thus, here we have two expressions of the capacity of concrete to resist shear in absence of torsion, and whichever gives the smaller value, that value is assigned to Vc. Next, we are calculating the parameters E and EC, which are the ratios of the torsion and shear. E is the ratio of the ultimate torsion to the ultimate shear, and EC is the ratio of the capacity of concrete to resist torsion to the capacity of concrete to resist shear. Note that this E is not the eccentricity of the CGS. The parameters E and EC are used in the interaction equation of the torsion and shear, from which we calculate the capacity of concrete to resist torsion and shear when both of them are acting together. Thus, in this step, we are calculating TC1 and VC1, where TC1 is equal to TC, the capacity in absence of shear, times E divided by E plus EC. We are limiting TC1 to half of the ultimate torque. VC1 is given as Vc times EC divided by E plus EC. Thus, now we have got the two capacities of concrete, one to resist torsion and the other to resist shear when both of them are acting together. Now we are calculating the amount of transverse reinforcement from the expression of ASV by SV. ASV by SV is calculated from the greater of the two expressions. The first expression is based on the skew bending theory, where ASV by SV is equal to the equivalent flexural moment MT divided by 1.5 times B1 times D1 divided by Fy. Again, here B1 is the smaller dimension between the longitudinal bars, and D1 is the larger dimension between the longitudinal bars. The second expression of ASV by SV is from the requirement of total shear, where ASV by SV is equal to AV divided by SV. This is the requirement based on flexural shear plus 2 times AT divided by SV. This AT by SV is the requirement based on torsional shear. They are considered to be additive in both the legs of the shear flow zone, and from which we calculate the second value of ASV by SV. Now, from the two expressions of ASV by SV, we are selecting the higher one to determine the amount of transverse reinforcement. In the previous expression, AV by SV is calculated from the shear to be carried by the steel, which is Vu minus Vc1, and that divided by 0.87 Fy d1 gives the shear to be taken by the steel, which is AV divided by SV. The second expression is for the torsional shear, where the torsion to be carried by the steel is Tu minus Tc1, and that divided by 0.87 Fy times B1 times D1 gives the amount of transverse reinforcement to carry the torsional shear. These two are combined to get the value of ASV by SV. In this previous expression, B1 is the distance between the corner longitudinal bars along the short side, and D1 is the distance between the corner longitudinal bars along the long side. Now these values at the beginning are not available exactly, but these are estimated based on cover requirements and estimated size of the transverse reinforcement. We have to satisfy the minimum amount of transverse reinforcement. The minimum amount of stirrups is given by the following equation: ASV divided by B times SV is equal to 0.4 divided by 0.87 Fy. Again, we need a minimum transverse reinforcement so as to check a sudden failure due to the shear which is generated by flexure and torsion. The seventh step is calculate the maximum spacing and round it off to a multiple of 5 millimeters. The maximum spacing is governed by both shear and torsion. It is 0.75 dt or 4 bw for shear and x1 plus y1 divided by 4 or 200 millimeter for torsion. Select the smallest value. Thus, there are two requirements of maximum spacing. The first one is for shear, which is based on the plane truss analogy. For shear, there is a maximum limit of 4 times bw to that. The second requirement is for torsion, and that is based on the space truss analogy for torsion. There also we have a maximum value of 200 millimeters. Once we calculate these 4 values, the smallest value gives the maximum spacing for the transverse reinforcement. The eighth and the final step is to calculate the size of the stirrups based on the amount required. Once we know SV, from the value of ASV by SV, we can calculate ASV, and from there we calculate the size of the stirrups and the number of legs that will satisfy the value of ASV. This whole procedure can be done for other sections if we need to vary the amount of longitudinal reinforcement as well as the stirrups. It depends upon the designer that how many sections we are designing for in a particular beam. Let us understand the design procedure by the help of an example. Design a rectangular section to carry the following ultimate loads. Tu is equal to 44.5 kilonewton meters, Mu is equal to 222.5 kilonewton meters, including an estimate of self-weight. Note that here the value of Tu is substantially small than Mu. The flexural shear Vu is equal to 89 kilonewtons. The material properties are as follows: Fck is equal to 35 Newton per millimeter square, Fy, the yield stress for both the longitudinal and the transverse reinforcement, is equal to 250 Newton per millimeter square, Fpk, the characteristic tensile strength of the prestressing steel, is equal to 1720 Newton per millimeter square, and the intended prestressing is Fpe is equal to 1035 Newton per millimeter square. This value is the effective prestress after the losses. The first step is to calculate the equivalent moment Me1. For the rectangular section, let the depth divided by the breadth be equal to 2. This gives an economical rectangular section. With this value of d by b, we can calculate Mt, the equivalent torsional moment, from the Tu, and substituting the values of Tu and d by b, we get Mt is equal to 99.5 kilonewton meters. Thus, Me1 is equal to Mu plus Mt, which is equal to 222.5 plus 99.5 is equal to 322 kilonewton meters. What we note is that in presence of torsion, we are designing for a higher flexural moment as compared to the original flexural moment. The original flexural moment was 222.5 kilonewton meters. but in presence of torsion we are designing for a moment which is 322 kilonewton meters. The second step is to select the section and design AP and AS. For the rectangular section, going by the preliminary design and final design steps, we are coming to this result with B is equal to 250 millimeters, the total depth is equal to 500 millimeters, the effective depth D is equal to 450 millimeters. Provide 2 of 16 millimeter diameter corner bars. The flexural design results are as follows. AS is equal to 2 times 201 is equal to 402 millimeter square. Required amount of prestressing steel with dP is equal to D equal to 450 millimeters is AP equal to 484 millimeter square. The design has been done based on the steps that we do for a conventional flexural design. We first, based on the preliminary design, we selected the dimensions of the sections. We found the amount of the prestressing steel based on some non-prestressed steel which we need for holding the closed stirrups. This is actually a partially prestressed design where we are taking advantage of the longitudinal steel to have the flexural capacity. And based on the design, we have found that the amount of non-prestressed steel is 2 of 16 millimeter diameter bars, and the amount of prestressing steel whose depth is considered to be same as the effective depth of the non-prestressed steel is 484 millimeter square. Provide 11 millimeter diameter strands with area 70 millimeter square. Thus, at this stage we are selecting what type of strands we shall use for prestressing, and the required number of strands is equal to 484 divided by 7 is equal to 6.8, which is rounded off to 7. Provided amount of prestressing steel is AP provided is equal to 7 times 70 is equal to 490 millimeter square. Thus, the amount of prestressing steel for the primary longitudinal reinforcement has been designed at this stage, and it is 7 of 11 millimeter diameter strands. The third step is to calculate the other equivalent moments, ME2. Now, in this example, MU is larger than MT, and hence design for ME2 is not required. The fourth step is to calculate ME3. Here, since MU is larger than MT, design for ME3 is not required. In most of the situations, we may not have to design for ME2 and ME3 because the flexural moment is substantially high compared to the equivalent moment due to torsion. But there may be cases where the equivalent moment is high, and in that situation we have to design for ME2 and ME3 as well. Now we are moving on to the design of the transverse reinforcement. Calculate TC. First we are calculating FCP, which is the average pre-stress in the section. The average pre-stress is calculated as PE divided by A, which is equal to FPE times AP divided by B times the total depth. Substituting FPE is equal to 1035 Newton per millimeter square, AP is equal to 490 millimeter square, B and D are 250 and 500 millimeters respectively. We find that PE is equal to 507,150 newtons and A is 125,000 millimeter square. Thus, the average pre-stress in the concrete is equal to 4.06 Newton per millimeter square. Since we are interested in the numeric value, we are not placing the sign in this expression. We have found that FCP is less than 1/3 that of the characteristic strength. The characteristic strength is 35 and 1/3 of it is about 12 Newton per millimeter square, and the average pre-stress has been limited to the 30% of the characteristic strength. With the value of FCP, we are calculating the value of lambda p, the multiplying factor to consider the effect of pre-stressing force. Lambda p is equal to 1 plus 12 FCP divided by FCK is equal to 1 plus 12 times 4.06 divided by 35 is equal to 1.55. Thus, the effect of pre-stressing force is considered by a multiplying factor which is 1.55. That means 55% of the strength has increased due to the presence of the pre-stressing force. Thus, the value of Tc is equal to 0.15 times 250, which is the value of B, then 250 squared times the value of D, which is 500, times 1 minus 1 divided by 3 times 2, where 2 is the value of D by B, times 1.55, which is the value of lambda p, times root over 35, which is the value of the characteristic strength. This gives the value of Tc is equal to 35.8 kilonewton meters. That is the capacity of concrete to resist the torsion in absence of any shear force. To calculate Vc, we are first calculating the value of, say, VCR. For that, we need the amount of pre-stressing steel as a percentage. 100 AP divided by BD is equal to 100 times 490 divided by 250 times 450 is equal to 0.43% of pre-stressing steel. From table 6, for M35 concrete, tau C is equal to 0.46 Newton per millimeter square. The value of the pre-stress at the level of the CGS is equal to minus PE by A minus PE times E square divided by I. This expression is again available from the stress concept, and once we substitute the value of PE, A, E and I, we get the value of FPT equal to 11.85 Newton per millimeter square. Here E has been estimated as the depth of the pre-stressing steel minus the depth of the CGC. 450 minus half of 500 gives 200 millimeters, and I is equal to BD cube divided by 12, which is 2.604 times 10 to the power 9 millimeter to the power 4. The value of M0 is equal to 0.8 times FPT times I by Y, and once we substitute the value of FPT, I and Y, we get M0 is equal to 123.43 kilonewton meters. Thus, substituting these values of the tau C, M0, Vu, Mu, we can calculate VCR is equal to 84 kilonewtons. Thus, this is the amount of shear that will generate a flexure shear crack. The value of Vc0 is equal to 0.67 times 250 times 500 root over Ft, which has been calculated as 0.24 times root over 35 is equal to 1.42 Newton per millimeter square. Substituting the values of Ft and Fcp, we get Vc0 as 215.6 kilonewtons. Here Vc0 is much higher than VCR, and hence we are assigning the value of VCR to Vc. Thus Vc is equal to 84 kilonewtons. We are calculating the parameters E and EC. E is equal to Tu divided by Vu. After substituting, that comes out 0.5 meters, and EC is equal to Tc by Vc, which By substituting the values of TC and VC, we get EC is equal to 0.43 meters. From this, we are able to calculate TC1 and VC1. TC1 is the reduced value from TC. The original value of TC was 35.8. From this, we get a reduced value. TC1 is equal to 19.26 kilonewton meters. Similarly, we get a reduced value of VC1 from VC. Thus, 84 kilonewtons has been reduced to 38.84 kilonewtons. Here, TC1 is less than TU by 2, and hence it is okay. We are calculating ASV by SV from the equivalent moment, and we get ASB by SB equal to 3.3 millimeter square by millimeter. B1 has been estimated as 250 minus 50 is equal to 200, and D1 has been estimated as 400 millimeters. For the second expression of ASB by SB, we are calculating from the shear to be carried by the steel, and once we substitute the value of VU and VC1, we get AV by SV is equal to 0.58 millimeter square by millimeter. From the torsional requirement, AT by SV is equal to 44.5 minus 19.26 divided by the values of the variables gives 1.45 millimeter square per millimeter, and once we substitute that in the expression of ASV by SV, we get a requirement of 3.48 millimeter square by millimeter. This is higher than the previous requirement, and hence we are selecting this value for ASV by SV. We are checking the minimum amount of stirrups, which is given as ASV by SV is equal to 0.4 times 250, which is the value of B, divided by 0.87 times 250, which is the value of Fy, gives 0.46 millimeter square. Thus, the governing value of ASB by SB is 3.48 millimeter square by millimeter, which satisfies the minimum requirement. We are calculating the maximum spacing SV, and in this case, by estimating x1 and y1, we get a maximum SV of 156 millimeters. The other values of SV do not govern. We are selecting the size of stirrups as 2 legs of 12 millimeter diameter stirrups. Thus, ASV is equal to 2 times 113 is equal to 226 millimeter square, from which we get SV equal to 65 millimeters. Thus, our design section is shown here, with the stirrups is 12 millimeter diameter stirrups as 65 millimeter on center. We are providing 4 corner bars with 60 millimeter diameter, and we are providing 7 number of 11 millimeter diameter strands with PE is equal to 507.15 kilonewtons. Thus, today we covered the detailing requirements for torsional reinforcement. We studied the general comments on the torsional reinforcement, and we also studied the design for torsional reinforcement. The design for longitudinal reinforcement is similar to the flexural design for a prestressed section, and the design of the shear reinforcement is similar to the stirrup design that we had seen earlier. With this, we are ending the design for torsion, and in our next module, we shall look into the serviceability requirements for prestressed concrete sections. Thank you.